as you heard earlier, this is a presentation that has been given earlier. And I am the tunnel safety officer for the Swedish Transport Administration. And the topic today I will talk about is safety concept in Swedish road tunnels, which nowadays includes fixed firefighting systems quite a lot. And I will talk about this for about 30 minutes. So how come that we started to look at fixed firefighting systems in Sweden? It's because of water, but not because of water in the fixed firefighting system, but water that stop our roads. This is a picture of Stockholm, and you see there's a lot of water, and that means you have to build a lot of bridges. And bridges are expensive, so you don't build enough of them. And then the bridges looks like this, and it has done this for a lot of decades, as you can see on the pictures. And the solutions for that in Stockholm is to start digging tunnels and go underground and bury the cars. And as you can see, it's three generation of tunnels, more or less, in the Stockholm area. First, we have the Southern Link tunnel in the south of Stockholm that opened for traffic in 2004. So it's been in use roughly for 20 years now. And then we have the Northern Link up in the northern end of the city center, open for traffic in 2015, roughly 10 years later than the Southern Link. And then we have the big bypass Stockholm in the west of the suburbs. It's a huge tunnel that will be opened in 2030. So that means it's about 10 or 15 years between the big tunnel projects. So that gives us time to estimate and develop the safety concepts from each tunnels. So we have three generations of tunnels here, and I will describe how it has developed over the years. And the Swedish tunnels are a bit different from other Scandinavian tunnels because they are in urban environments, a lot of dense traffic. So it's not like the Norwegian or Faroe Islands where you have rural tunnels with very little traffic. So it's two different extremes of road tunnels. So if we start looking at the Southern Link, open for traffic in 2004, it was equipped with pretty much state-of-the-art. It had all types of safety equipment that was relevant at that time. Short distances between escape routes, 100 meters, and quite a lot of water for the fire brigade, 2,500 liters per minute. It was to be able to cool down a gas tanker with the two oscillating water cannons, because all types of hazardous goods are allowed in those tunnels. And quite a lot of other safety measures as well. As I said, pretty much state-of-the-art. So the safety concept in those tunnels, it's parallel tunnels. It's just one direction in each tunnel tube, and there's a short distance between the tunnel tubes. So there are short cross passages that are escape routes, and they are also fire locks. There are 4 doors in each of those locks. And this means that the parallel tunnel tube is the safety place for evacuating road users, and also a safe place for the fire brigade and the ambulance to start their operations. So we never go in with the fire vehicles, the fire brigade's vehicles in the tunnel where you have the fire. We also always go to the opposite tunnel tube. And since we have this short distance between the escape routes, we always do the attack on foot with the fire brigade. And this is quite a common safety concept for all the Scandinavian tunnels, I would say. And we also have longitudinal ventilation in those tunnels, so we push the smoke in the direction of the traffic. So we have different information for different parts of the tunnel. We have information signs in the ceilings. So you give different messages depending on where you are considering to the fire. So, but there's a problem when you have a lot of urban traffic and you have longitudinal ventilation, because if you want to have a safe tunnel, you really need to have a free flow. You can't have congestions, because the safety concept, it builds on that the traffic downstream from the fire moves on quicker than the smoke, so they can evacuate, leave the tunnel before they end up in critical conditions. And the cars that end up upstream, they are supposed to stop when they come to the fire, and then they stand in a fresh air coming from upstream, and they can evacuate in a safe manner. So this is a nice safety concept in theory. When the Southern Link opened for traffic in 2004, it was designed for 60,000 vehicles a day. The first weeks we had 100,000 vehicles per day, and a lot of heavy goods vehicles. So that means we have slow traffic. We did not have this free-flowing traffic that was needed for to have a safety concept. So if you have a large fire, we could end up with this situation. And that is not considered to be acceptable. Therefore, the tunnel entrances are closed when we get slow-moving traffic in the tunnel. So the tunnel cannot be used when it's needed the most. So when we shut down the tunnel, the Southern Link tunnel, that cost, the socio-economic cost is about 1 million Swedish crowns per hour. And this is done several times every week in the rush hour. So this is what it looks on the surface. Of course, when you shut down this type of main road when it's needed the most, of course you get even more congestions on the surface road network. And this was not accepted when it was time to look at the next big tunnel, the Northern Link tunnel project. The politicians in Stockholm said, no, you have to design a tunnel that is able to deal with slow-moving traffic and congestions. The problem is that they said that in a very late stage of the tunnel project. The tunnel was more or less already built. So that's when I came in contact with the project about 2008, 2009. So we started to look at what is the problem with having traffic downstream from a fire. Here you see the fire sizes to the left, and then you see what we estimated the consequences from evacuation property and socioeconomical means. So it was the evacuation problems that really was the designing our safety concept, but the choice of safety concept always also did give us benefits when it came to saving property and the traffic disturbances. So what you can see here is that about 10 megawatts, that's where we get some kind of tipping points. We don't want to evacuate people when we have more than 10 megawatts in the tunnel. Then we are reaching unacceptable conditions, critical conditions. So that means when you look at the fast fire curve in the tunnel, here you have the fire size. For some reason, it's in kilowatts instead of megawatts, but you see where you have 10,000 kilowatts, that's the 10 megawatts. And you reach that after about 8 minutes. when you follow the fast curve. And that means that the evacuation has to be done by then. So there's a lot of things that has to happen during those 8 minutes to be able to get all people out of harm's way. And the last 4 minutes in this time table is a bit, it's difficult for us to make the road users doing what they are supposed to. When it comes to the first 4 minutes, then we have control of things. We know what type of systems we have to detect the fire. We can start our action plans, and we can train our operators in the traffic control center, but we can't train the road users to do the right thing. So that's where we have the problems, especially in the middle orange box, to make them use the right users, make the decision, use the correct decision. So therefore, we started to look at fixed firefighting systems, just to buy ourselves time when it comes to the evacuation. So if we could activate the fixed firefighting in an early stage, after perhaps 3 or 4 minutes, then we may never could get the fire bigger than these 10 megawatts that we regarded as critical. So then we have very much time for the evacuation. Perhaps we never reach critical conditions in the tunnel. So therefore, we started to look what we could do in the Northern Link. This is more or less a retrofit. As I said, the tunnel was more or less already built when we started to look at these issues. So we had to use the existing fire hydrants to try to make a fixed firefighting system. So we had a tight budget. They said that you could only spend about half the amount of money that the traditional systems on the market costed, water mist systems and so on. So that meant at 2008, we had about 0.5 million euros per kilometer in the hardware installations to spend. We were not allowed to delay the project, and we also had to create the minimum of maintenance in the tunnel. And it's okay to departure from the sprinkler regulations. We did not have to follow the sprinkler norms. And of course, it had to cope with winter conditions. So when we look at safety issues in road tunnels, I think this curve is quite significant. It comes in almost every discussion you have. You have the safety at the y-axis and the cost at the x-axis, and the more safety you have, the more it costs. And what you should try to achieve is to get as much safety per crown or per euro. Because when you reach a certain point, you want to increase the safety with perhaps 10%, then you end up costing twice as much. And the question is that well spent money? So this was a perspective that we tried to have when we designed the sprinkler system for the Northern Link tunnels. We didn't even call it a sprinkler system, we called it fixed firefighting system, or brandbekämpningssystem in Swedish, just because we did not want to tie our hands on the back with the sprinkler regulations. That would push us far up on this curve. Because we don't think that the sprinkler regulations are adapted for the road environment. It's more warehouses and that sort of things. So our solution was sidewall throwing nozzles. This is Tyco SV24 we end up using. We put it in the center of the ceiling and they throw sidewalls, so they are put back to back. And they fill the cross section in a quite nice way with the water spray. And this is how we connected to the existing fire hydrants. We just built onwards. This is in each escape route. You have this type of valves to control the fixed firefighting system sections. And this was a big deviation from the sprinkler norms. You are not supposed to use the same water pipes for the fire brigade and for the fixed firefighting system, but it's very cost effective to build like this, especially in a road tunnel when there are long distances. So this was the layout of the pipes, because the costs of a fixed firefighting system, that's pretty much the amount of meters of piping you have to put in the tunnel. So this is the most cost-effective layout that we could end up with. There are 150 meters between the escape route, so that means every section is 75 meters long. So when we have a fire, we activate this 75 meters. Or if we have the fire between the sections, we could activate 2. But then we don't have enough water to have the dimensioning water density. We look at having 5 millimeters per minute when we activate one section. But when we have 2, we get a bit less. But on the other hand, we get larger droplets because there are less pressure, so that we still have quite an efficient section when we use it like this. This is the type of pipes that we used, plastic coated on the inside and the outside and on the ends. So there are no exposed steel for the environment anywhere. This is for corrosion reasons. We have very high corrosion standards in our road tunnels. It's C5 marine demands. It's the same that you have in the offshore industry. This is the type of couplings that connects the pipes. And as you can see, you can use just a fixed spanner to connect them, so you don't have to do any welding or anything to build this type of systems. It's almost as if IKEA had designed the concept. You just need one tool to build it. And these are the brass T-couplings that the nozzles are attached to, and they are made out of casted in brass, because the sprinkler nozzles are also in brass. So to avoid galvanic corrosion, we wanted to use the same material, and that has worked very well. So this is what it looks like in the tunnel, the Northern Link. Since we have plastic coating on the pipes, we could choose the colors of the pipes so they blend in the background. And of course, this was a new concept, so we did quite a lot of testing. And we have very good help of Mr. Höker Ingason at SP, nowadays RISE here in Borås. And of course, we did a lot of water distribution tests in different air speeds, and the visibility, that was a big issue, because we wanted to activate the systems immediately, even before the traffic has stopped. So therefore, we looked at visibility both from evacuating by foot and driving cars through the activated section. And of course, fire tests, we had to prove that the concept actually could fight the fires. It was 5 millimeters per minute was regarded as quite a low water density, but we proved that that could be quite effective. And of course, winter conditions. We tried full scale at -6 degrees to see what happens. And corrosion, as I said, that's a big issue. So we tried the different components in Swerea Kimab's testing laboratory, corrosion laboratory. This was the so-called Volvo test that was conducted, and we thought it was acceptable. And at the same time as we were doing this test for the Northern Link, we had one of our consults, Mr. Konnebecker. When we reached the end of the day in the laboratory in Borås, he opened his briefcase and took up something. He said, "I did this last Saturday in my garage." And that was the prototype you see at the picture. It was a much larger nozzle than anything that accepted on the market. He has modified one existing nozzle. And just for fun, we attached it to the test rig and you let it spray, and it was an amazing efficiency. It spread the waters about 18 meters from wall to wall, and it gave about 10 millimeter per minute and very large droplets. So it was a very striking nozzle. So that one was decided immediately to be used in the next big tunnel project in the bypass Stockholm. So we contacted the Tyco, the sprinkler manufacturer in USA, and they agreed to build the product out of this prototype nozzle, and it's called the TN25 nozzle. And it's now being used in some tunnels around in Europe and in Sweden. So here we see some different test results. We burned some wooden pallets down in Rice fire laboratory. And you see the blue line, we had free burning. We reached 1.7 megawatts, and with the SW24, that's 5 millimeters per minute, the green one. You control the fire. It didn't grow, but it also doesn't reduce the fire size, but it controls the fire. But then the red line, that is the new powerful TN25 nozzle. You can see that it reaches suppression quite effectively. You see the difference on the pictures on the screen as well. This is the same time at these different tests. I think it's about after 6 minutes or something like that. The picture to the right is the 5 millimeter per minute, and to the left you see the much smaller fire with the TN25 nozzle. But here is some test results from another tunnel, in the Törnskogs tunnel. We used a gas burner and longitudinal ventilation. I think it's about 6 meters per second. And we had a steel plate that with a thermal element that recorded the temperature. And you can see in the diagram what happened. We had free burning. We had to turn the burner off at about 350 degrees after 4 minutes. Otherwise, we would have destroyed the equipment. But in the other tests, we activated the fixed firefighting systems after about 3 minutes, and you can see you immediately cool down the steel plate. And the effect is exactly the same, no matter if it's 10 millimeters per minute or 5 millimeters per minute. So I think this proves that you are safe from spread between vehicles when you have this type of systems, no matter what water density you use. You don't need to be afraid of having spread to other vehicles inside the water spray. Here's another important test result. We looked what happened if we have a burning fuel spillage. There's always discussions about, oh, you should never put water in a gasoline fire because it boils up and things gets worse. But that was not what happened when we did these tests, because there are such a thin layer of fuel, gasoline, when it floats on top of the water. So you never get to the point where you boil the water under the fuel, because you always keep getting more and more water, so you keep the water cool all the time. So what happens is that the fuel floats on top of the water and it keeps burning, and you can see the effects here on the diagram. You don't get much reduction of the fire size, but you don't make anything worse either. So this was very important. This shows us that it's safe to activate the system no matter what type of fire you have. Even if you have a petrol tanker that has crashed, you can activate the system to protect the vehicles around and cool down the surroundings and prevent the fire from spreading to the rest of vehicles in the tunnel. And we did full-scale tests in Runehammer tunnel as well. Here you see some typical test results. We let it grow to 20 megawatts. If it was free burning, it would have reached about 100 megawatts. It's 420 wooden pallets. It's supposed to simulate a full loaded heavy goods vehicle. And you can see at 20 megawatts, when we activated the system, you immediately get a reduction of the fire size. And after a while, you reach suppression. And you see in the picture in the bottom that there's a lot of unburnt fuel left. And this is a very good result for this type of tests and this type of facilities. If you use water mist system and try to do the same type of test, you will end up with a lot more burnt wooden pallets. So the experience is after 10 years of operating the systems in the Northern Link. Here you see what it looks like when you drive through it without using your windshield wipers. You see over 50 meters. And you can see the road surface. And if you start the windshield wipers, you get a lot better visibility. Here you see what it looks like when you're just standing outside the vehicle and looking at the activated section. And the person you see in the picture, I think he's at the other end of the section. And you can also see the lights from the escape routes quite a far distance away. So here is a 75-meter long sections that you can see straight through. And if you compare this to the visibility in a water mist system, I would say it's quite a big difference. And this is quite important, as I said, because we want to evacuate this system immediately. Once you have verified that there is a fire in the tunnel, you just start action plans, which starts the fixed firefighting systems. So there has been a lot of discussions about the problems with freezing. That has been one of the main issues about fixed firefighting systems in road tunnels. In the Northern Link system, we had a dry system, an empty system in the road tunnels. So there is no water at all. And it's self-draining. It's built so it just pours out all the water by itself. So and when you activate it when in winter conditions, it is not slippery on the road because the water heats up the tarmac rather than the tarmac cools down the water, because you always keep pouring on more and more warm water, or more, it's not really warm, but warmer than the road surface at least. And there has been no problem with icing in the nozzles, because they are very large holes in the nozzles and the high flows of water. But once you turn the system off, then you get freezing on the road surface. So you have to do some kind of put sand or something on it once you want to open the road for traffic again after the fire. And this isn't the only place where you use fixed firefighting systems in winter conditions. You have wooden churches, you have offshore industry, you have sawing mills, parking garages, etc., etc. So the freezing, it's not. It's an issue you have to take care of, but it's not. It's possible to use it anyway. And here we have an example from the Northern Link. We have a fire, and you can see how there's about 1 or 2 minutes between these pictures on the top, and you can see that the traffic is moving. Even though they are supposed to stop, there are red crosses on the signs on the ceiling, so they are breaking the law here, but everybody just keeps driving through the activated section and out of the tunnel. But you can see how much the fixed firefighting system has reduced the fire size. And then you see the fire brigade goes in and do the final extinguishing of the fire, because you can never extinguish the fire completely by pouring the water on the outside of the vehicle. You have to go in and manually finish off the fire. And here's another example. It's one of the biggest fires we've had in Sweden so far. It's a camper van, and this is what Mr. Höker Ingasson has said after looking at the pictures of this fire. So he said, all right, it's about 10 megawatts on the pictures. This is what we have with the fixed firefighting system. But then we asked him to estimate what it would have been without the fixed firefighting system. And then he said that it would probably reach about 30 megawatts. And it would be a lot more of fuel that would have been burned. It would have been a lot more total energy that has been released in the tunnel. And with the 30 megawatts, we would have get quite a lot of damages in the tunnel. Now, this case, when we just had 10 megawatts, we could open the tunnel for traffic after just 2 hours. That would not have been possible with 30 megawatts. So if we look at this picture again, the difference between 10 and 30 megawatts is quite important, especially when we look at the disturbed traffic. If we said we had 30 megawatts, we could have it closed for weeks. And as I said, on the Southern Link case, it cost 1 million crowns per hour to have it closed. It's socio-economical. And you can, well, just do the math and see what it ends up in weeks. So maybe the system has already paid off socio-economically just by keeping this fire down. So this is what it could look like when you have a large fire in a tunnel without fixed firefighting system. This is from February this year in Wyoming, USA. When you have dense traffic and you have a lot of queues, so you have fire spread between the vehicles. So, as I said, the socio-economical part is quite important. It's very expensive to shut down the Southern Link. There has been calculations done. It costs 50 million crowns per year, the traffic disturbance, just because shutting the tunnels down in the Southern Link. So if we spent 400 million Swedish crowns to put a fixed firefighting system in the Southern Link, it would pay off in just 8 years in a socio-economical way, just by reducing the traffic loads on the surface road network in the rest of the city. And to that comes the savings of fighting the fire itself and reducing the damages in the tunnel. We have about one fire each year in the Southern Link, so even there it would do quite a lot of good. So we are now looking at means to put in fixed firefighting also in the Southern Link to a retrofit. All right, time is rushing. We have another black sheep in Sweden when it comes to tunnel safety. It's the Muskö tunnel. It's an old tunnel. It reminds quite a lot of the type of rural area tunnels that you find in Norway, Faroe Islands. It's a bidirectional, 3,000 meters long subsea tunnel. No escape routes, just a hole in the ground. And here again, I would like to give Mr. Höjkeringason at RISE a lot of credit. He is speaking very warmly about this type of system to use automatic glass bulb sprinkler in the road tunnel. There are a lot of advantage in using that. You can make a very cheap installation. You don't need to feed the sections with a special pipe. You don't have any section valves. You don't need a special detection system. You don't have to do some work to position the fire. You don't need any activation from any traffic control center. The system just works autonomously. And there are some challenges with using this type of systems in the tunnels because it could be sensitive for high air speeds. That was the reason we did not use this in the Northern Link tunnel. Because in this type of one-directional tunnels, we could reach quite high air speeds because of the piston effects. So we could have 6 up to 10 meters per second. But when you have bidirectional traffic, you don't get the same type of piston effects. So there are lower air speeds in these type of tunnels. So we looked at this concept for the Muskö tunnel. Could this be developed? RISE and SP has done quite a lot of research. There are 3 different reports about this type of system. And there has been done some theoretical calculations of fire sizes, air speeds at different downhill. And we did distribution tests on different nozzles, and there has been done some practical scale tests, 1 to 3, in container tunnels. It was 50 meters long. And the results of this has been presented in the paper in ISTSS 2020, and it's also been an article in Fire Safety Journal. So the research is academical, very high quality. And this is the tests that we did. We had a 50-meter long container tunnel with a 2 meter per second fan. And we varied a lot of parameters, the time for or the temperature that the nozzles activated in, and we had different air speeds and different water pressures. So there were some setups that did not work very well, but we also had some very interesting results. This test number 2, for example, that I show here is quite impressive. The figures you see in the table here is the time it takes before the nozzle opens. So we had the first nozzle activated after 3.5 minutes, and then the 3 more after about 6 or 7 minutes. And 10 minutes later, 1 more opened. So that means we had 5 nozzles opened over a 25-meter zone, and they consumed about 2 cubic meters per water, and it gave a water density of about 10 millimeters per minute, which is quite a lot. And this was enough to contain the fire. So here you see a result. We have about free burning, we have about 60 megawatts, but with these test results, we ended up just having 16 megawatts. So the system was quite successful here. And well, here you see some temperature results as well. We get temperatures at about less than 100 degrees at the levels where evacuating people are walking. Well, I don't want to spend time is rushing. So the conclusions of this concept is that it's efficient and the theoretical calculations matches the test results. That's very nice. And the system did not open too many nozzles. It just opened 5 nozzles at this very good test. And that means it does not use that much water. And the fire is controlled before the thermic, before you get too high air speeds in the uphill climbing. And you can use the sprinkler nozzles off the shelf. They are already on the market. So here's the concept for the Moska tunnel. We use automatic sprinkler with glass bulb, and we use it pointing upwards because we don't want to risk that it's damaged by loads from high vehicles. It's a 3-kilometer long connected section, and we are pumping seawater through the pipe continuously, just to, at least in the wintertime, to reduce the risk of freezing. In the Moska tunnel, we also today pump in warm air to reduce the risk of freezing in the drainage water that comes into the tunnel. So we think the risk of freezing is not very big. And then I was asked to look at the similar concept at one of the Faroe tunnels. I'm not even going to try to pronounce the name of this one. I will just call it the S tunnel, I think. And this tunnel is 23 kilometers long. It's about 180 meters deep under the surface of the ocean. And that's an issue because then you have a difference in pressure in the pipes that you have to deal with. You have to put in some sort of pressure reduction valves. So that's a complicating issue, but it's not impossible to do. And you also have some sort of water supply at the entrances of the tunnel. I think this is sweet water, not salt water. So a rough estimation of the costs end up with 115 million Norwegian crowns. So let's say 200 million Norwegian crowns, which give us about 8 million Norwegian crowns per kilometer. And the maintenance is perhaps 1 million Norwegian crowns per year. Much depending on the solutions for heating, if you need to use electricity to heat the water or not. So in Norway and somewhere I heard in Iceland as well, you use safety chambers or escape chambers, to secure the safety in the tunnels. That perhaps is the alternative to put in a fixed firefighting system in these type of tunnels. And the concept I have seen is a distance of 500 meters between the chambers. They are 30 square meters, just about, and there are pressured air in the steel tanks for 3 hours. And that requires an offensive operation from the rescue services, and you have to have a efficient reversible ventilation that really can turn the direction of the smoke. And the cost of these escape chambers depends on what sources you look at and who do the calculation. Between 2 and 17 million Norwegian crowns per kilometers is what I have found. And they need some sort of maintenance every second month. So I would say this type of solution that's quite in this green zone of the curve I described earlier. It's not a perfect system. There could be a situation where 500 meters is a bit long. Perhaps 30 square meters could be too small if you're unlucky. Perhaps 3 minutes is not enough, but probably all these figures are sufficient. But it's not 100%. So if you compare the benefits of the rescue chambers and the fixed firefighting system, when it comes to personal safety, I would say that they are comparable. They both have a good effect, but none of them are 100%. When it comes to cost, they are also comparable. Big uncertainties, of course, in the mathematics, but roughly that's the same part of universe at least. But when it comes to cost benefit, then I would say it's a clear advantage for the fixed firefighting system, because you also protect the facility itself. The downtime that you have in the tunnel is shorter, so the socio-economical cost is less. Because we have seen it could look like this in the tunnel after a big fire. And you could have this when you have escape chambers also. So if I was a tunnel operator, I would definitely consider fixed firefighting system if I was told to put in the rescue chambers. But that's not my choice to do. Okay, thank you. A bit over time, maybe.
Thank you. I think we have maybe room for 1 or 2 questions. I'll start myself. How does it handle electric vehicles? We have a growing more and more vehicles in Iceland, at least, are electric, and you hear those bad stories about the batteries.
Yeah. Of course, when you put water on the outside of an electric vehicle, you don't do much for the battery safety, but you do reduce the total fire size of the vehicle in the same way as you do in a normal car. And the difference in fire size between an electric vehicle and an old-time car is not that big. We have about 5 megawatts in both of those cases.
Mm-hmm.
So what you get when you have an electric car, you could have a longer fire to deal with, because it's more difficult to put out the fire. But I don't think we'll see bigger fires, at least not as long as we're talking about just normal cars. When we talk heavy goods vehicles, then it's another story, but we are not there yet.
Okay.
Are there any questions from the audience? No? I think we can thank you again, Ulf.